Awesome. Thank you, Emily. And thanks to all the organizers of this workshop, and thanks to the IPAM workers who have just been doing an incredible job navigating this massive Zoom workshop. So this is based on a paper that Leonard Huang and I published this past March, but it contains some stuff that we've not yet put on the archive. So in certain cases, I may be a little bit vague, but I'm happy to answer pretty much any question if you have one. Okay, good. So let's get started. So the goal of an ongoing historical problem is to classify all pairs of unbounded self-adjoint operators whose domains dA and dB are dense subspaces of some Hilbert space. So the goal is to classify these pairs of self-adjoint operators on Hilbert space that have nice domains, in the sense that the intersection of these domains contain an AB invariant dense subspace of the Hilbert space. And the reason we need that domain condition is that we would ask that the commutator of these two potentially unbounded operators acts on vectors from K by simply multiplying by I times the identity. So this is known as the Heisenberg Commutation Relation. So we'll call pairs A and B Heisenberg pairs, and we will also specify the space on which they satisfy the Heisenberg Commutation Relation. An canonical example of such a pair is called the Schrödinger pair. So if you have a one-dimensional quantum system with a single particle, you can represent that on the Hilbert space L2 of R. And without giving you the domains of P and Q, Q is an unbounded self-adjoint operator by simply multiplying F at some input X by the input X, and P is minus I times the differentiation operator, where, of course, that has its own proper domain of the Hilbert space. These two operators do satisfy the Heisenberg commutation relation on a variety of spaces, but one of them is the short space of rapidly decreasing functions. So P and Q form a Heisenberg pair, and they are the canonical pair that we'll talk about throughout this talk. So they get a special name called the Schrödinger pair. So in 1930, Marshall Stone asked if all Heisenberg pairs must be unitarily equivalent to some direct sum of copies of the Schrödinger pair. In other words, do we always have some unitary going from the Hilbert space H on which A and B are acting to some number of copies of L2 of R that intertwines A with Q and P with and B with P? And in 1931, von Neumann said no, but there's an asterisk there. So essentially what von Neumann did is he said that there's not a classification exactly for pairs of self-adjoint operators. However, you can classify unitary representations, pairs of unitary representations that are related to Heisenberg pairs. So in particular, if I have a pair R and S of unitary representations, I'll do it on a locally compact group G. So R is a representation of unitaries on the Hilbert space H, and S is a unitary representation of the dual group. And R and S satisfy what's called the Weil commutation relation. So if I switch the order of these two unitaries, I may do so, but at the price of multiplying by gamma of X. And this is for all gamma coming from the dual group and X coming from the group. So this is the Weil commutation relation. So these pairs are called Heisenberg representations. And von Neumann was able to classify these pairs. Maybe I also should say these are strongly continuous. You probably already thought that, but just to be clear, strongly continuous unitary group representations. Okay, so if I have a Heisenberg representation of some locally compact abelian group G, then you get unitary operator between H and some number of copies of L2 of G that intertwines S with U and R with V. And here, U and V are, I guess I should say, our U sub x's and V sub gammas are unitary operators on this Hilbert space. U sub x applied to some continuous function at an input y is simply translation by x, and applying V gamma to some input y is multiplication by the character gamma applied to y. Okay, so you can check that these two unitary representations do in fact satisfy the Weil commutation relation, so they form a Heisenberg representation, and this pair is known as the Schrödinger representation. So the reason this result has something to do with the original question that Stone asked about self-adjoint operators is because of Stone's theorem. So remember that if you have a self-adjoint operator A, then Stone's theorem on a Hilbert space, Stone's theorem says that you have a strongly continuous one parameter unitary group that you get from its functional calculus. And you can also think of this as though A integrates to that unitary group, because if you sort of naively differentiate e to the ix a and evaluate that at 0, you would get ia. So there's a relationship here. And also, if I had another self-adjoint operator B on that same Hilbert space, then B also would integrate to some sort of unitary group. And effectively, what von Neumann said is, hey, if I have a Heisenberg representation upstairs of these two unitary representations, then the Weil commutation relation that they satisfy actually pushes down to form a Heisenberg pair at the level of the what are called infinitesimal generators for those unitary groups. So you do get this direction of knowing that these unitary groups forming a Heisenberg representation implies that their infinitesimal generators form a Heisenberg pair. However, the times when you start with the Heisenberg pair and you want to integrate to a Heisenberg representation, that's not always a given. And so the corollary of the Stone-von Neumann theorem that is useful is essentially saying, if you know that your pair of self-adjoint operators integrate to unitary group representations that are a Heisenberg representation, then you do have a uniqueness statement about that Heisenberg pair. But essentially, this doesn't give any information about when this pair integrates. There are examples of pairs of self-adjoint operators that do form a Heisenberg pair, but do not integrate to a Heisenberg representation. And so a lot of research following this is dedicated to understanding essentially an integrability criterion or criteria for when you have this integration. So here is some of the research that has come out of that. If we start with a Heisenberg pair on some dense subspace K of a Hilbert space, it's well known already that at least one of the two operators, A or B, must be unbounded. In 2019, I showed that as long as that subspace K is a core for one of the two operators, then both of them need to be unbounded. There are examples of Heisenberg pairs where one operator is bounded. In 1958, Dixmier provided the sufficient condition on the subspace K that if you have a space K on which A and B satisfy the Heisenberg commutation relation, and K is nice enough that the operator A squared plus B squared is essentially self-adjoint on K, then you can appeal to the Stone-von Neumann theorem because that pair integrates and you have a uniqueness statement for A and B. And I should point out here, A subspace K contained in the domain of an operator is a core for that operator. If when you look at the restriction of the operator to that space K, and then you close that operator, you actually get all of A back. And of course, this is actually closing the operator, you're really closing its graph. But essentially, self-adjoint operators, it's not so much about the operator's action, it's more about the space on which the self-adjoint operator is defined that makes it self-adjoint. And so the core has to be a nice enough subspace of the domain that it remembers, that it's big enough and remembers enough about A to get it back when you close its graph. Also, an operator T is essentially self-adjoint if and only if it is symmetric, and in particular, it has a unique self-adjoint extension. So I'm sure a lot of people here are familiar with unbounded operator theory, but if you're not, it's possible to have a symmetric, densely defined operator in a Hilbert space that has a variety of self-adjoint extensions. Okay.
Before you go on, I think there are a couple questions in the chat that maybe are about the previous slide, if that's okay.
Got it. Thank you.
So Sam wants to know, is there a physical interpretation of being integrable?
That's a good question. So, I mean, this verbiage of like integrable is really coming from like a Lie algebra and Lie group relationship, saying that some relationship in the Lie algebra integrates back up to the Lie group. So I'm sure there is a good physical interpretation here, imagining A and B as observables in a quantum system, and then those unitary groups being essentially time evolution if you were considering them as Hamiltonians, I suppose. But I'd have to think about that to have a concrete physical.
Okay, and then there's a follow-up question, which is, Luca asks, are there physical applications of non-integrable pairs?
That's a really good question. I don't know that I've thought much about non-integrable pairs because I always want them to be integrable. So, I mean, here's an example of a non-integrable pair. If you have, basically you take what looks like the Schrodinger pair, but you don't look at it on L2 of R. You look at it on L2 of a closed interval, maybe from 0 to 1, and of course you have to make appropriate boundary conditions on the two operators so that they are still self-adjoint. But then on that space, Q, the multiplication operator by the input is now bounded. And so those two operators do not integrate, but of course I would think a quantum system on L2 from 0 to 1 certainly exists, thinking about particle in a box. So I think there are physical interpretations there for non-integrable pairs.
Great, thank you.
Yeah. Sorry, that was a long-winded answer.
Fantastic.
Thanks. Okay, great. Oh, and I did want to give a shout out to all of the many people over the last 90 years that have contributed to answering this question in the context of Hilbert space. So those are only a few. There are many, many more. All right. The integrability criterion that I want to focus on has to do with analytic vectors. So here's what an analytic vector for a linear operator on a Banach space is. A vector X is analytic if it is in the domain of all higher powers of that operator, and this series that involves applying powers of the operator to that vector actually converges absolutely. And so what you can think of here is literally imagine T being differentiation, and you're talking essentially about infinitely differentiable functions. So I can apply the derivative infinitely many times, but you have this extra condition of this series converging. And the way to think about that is if you do in fact have a relationship between the operator and some, I'll call it C0 group. So some group that represents translation with respect to the operator T, then having a vector be analytic for T, which I'll denote as script A subscript T, an analytic vector for T. This happens if and only if you have an analytic extension of that map on some strip in the complex plane about the real line. So maybe I'll just draw a picture instead of writing all those words out. So effectively, you have some strip containing the real line that function extends to. Okay, so that's what an analytic vector is. For an example of operators that have a lot of these, if you have a closed symmetric operator on a Hilbert space, then actually knowing that operator is self-adjoint or has a dense set of analytic vectors in the Hilbert space, those two notions are equivalent. So self-adjoint operators have a lot of them. And these analytic vectors for self-adjoint operators play a really important role in being able to integrate Heisenberg pairs to a Heisenberg representation. So Flotto and Simon, Snellman, and Sternheimer proved this essentially in the setting of Lie algebras and Lie groups. And then my collaborator Leonard Huang translated, I should say, into the setting of Hilbert space. So if you have a space K and it has analytic vectors for both A and B, and it's dense, then you do have this uniqueness statement because you can integrate to a Stone-von Neumann theorem application. Okay, great. So let's talk about Heisenberg pairs on Hilbert C-star modules. So the goal here is going to be stated almost verbatim. Classify all pairs of self-adjoint operators on a Hilbert C-star module. And I want the exact same domain condition, except, of course, I want this to be happening on some dense submodule of the Hilbert C-star module. The worst thing here is I haven't figured out how to make my slides do what they do and keep the writing. If anybody has any thoughts about that, I'm sure people have developed good techniques. Please let me know. Okay. So why would we even, other than just being mathematicians and wanting to do things in the most general setting possible, why would we want to try to classify Heisenberg pairs on Hilbert C-star modules? I'm going to give some kind of vague applications and things that I think are related, but these avenues haven't been super deeply explored by Leonard and myself. But for those of you who are interested in non-compact quantum groups, it's my understanding that unbounded operators on Hilbert C-star modules have a deep relationship with non-compact quantum groups. And the idea that, so this is a separate thought, the idea that Hilbert spaces are good places to represent quantum mechanical systems, Hilbert C-star modules provide a nice playground to represent quantum mechanical systems that have some sort of relativistic influence. And then, because we're all here at this workshop, I've seen a couple talks now that mention Hamiltonians and more quantum system inspired motivation for studying tensor categories and fusion categories. So there certainly seems to be some relationship there as well. Okay, and how are we going to go about doing this? Well, we're going to follow the exact same strategy that's been followed for the Hilbert space setting. The first tool that was derived was a Stone-von Neumann type of theorem, but we want to do that in the setting of Hilbert C-star modules. And secondly, we need to develop some sort of an integrability criterion for when Heisenberg pairs integrate to Heisenberg representations so that we can use the Stone-von Neumann theorem that we've built. I will go ahead and say the next slide, I will show you the Stone-von Neumann theorem that Leonard and I proved. It is only, unfortunately, in the setting of the C-star algebra being the compact operators. So our modules are over the compact operators. Of course, we would love if that were generalized further. Okay. So what we were able to show for a Stone-von Neumann theorem on Hilbert C-star modules is the stuff in purple I'll get to. So let's imagine for right now that we have a Heisenberg representation of a group locally compact abelian group G on a Hilbert K of H module. And we were able to show that any such pair is unitarily equivalent to a direct sum of copies of what I'm calling the Schrodinger representation on this particular Hilbert C-star module. So let me give you a couple of definitions. First of all, we have a Hilbert A module, and in mine and Leonard's setting, we do require that you start with a full Hilbert A module. You have a representation of your group, just as you did in the Hilbert space setting, that is strongly continuous or strictly continuous. For unitary representations, they are equivalent. And a representation of the Pontryagin dual. And you ask that this pair satisfies the Weyl commutation relation. Now, if you want a little bit more excitement, the part that I didn't mention is that Leonard and I were able to actually classify representations that also included some information about a C-star dynamical system, not just a group. So if you also have a non-degenerate star homomorphism of your C-star algebra acting as adjoinable operators, and you require that homomorphism and your representation of G form a covariant representation for your C-star dynamical system. And last, you require that the homomorphism of A and the representation of the dual group commute. Then this uniqueness statement that we've proven is true when A is the compact operators. So let me also tell you all the main players in the Schrodinger representation. So the canonical space Hilbert C-star module that our Schrodinger representations are represented on is this Greens and primitivity bimodule. I think actually Dave Penny's was talking about this Hilbert C-star module in the Ask the Expert session. So here, this is a right Hilbert A module, but the action on the right is twisted by the group action alpha. So that's our Hilbert A module. We have analogous unitary representations, where if I look at a compactly supported continuous function from G into the C-star algebra A, and I apply U sub X to that and evaluate at Y, this is almost exactly translation, except we will twist by alpha sub X. V is exactly the same definition as the Hilbert space setting. And then you can verify that this pair does satisfy the Weyl commutation relation. So we have a Heisenberg representation. And then if you want to classify the C-star dynamical systems when A is K of H, the appropriate representation for the Schrodinger quadruple that we're looking at is representing A just as left multiplication operators. And these these last conditions about covariance and commutation check out. Okay. So the main moral of this is this Stone-von Neumann theorem is a generalization of a concrete generalization of the classical one, but we would really love it if there was a classification when our C-star algebra A was something other than the compact operators. Okay, so now let's look at goal 2, which involves integrability criterion for our pairs of unbounded self-adjoint operators. So if I need to tell you briefly about some subtleties of self-adjoint operators on Hilbert C-star modules. So the domain of the adjoint of an operator, and this is actually true in Hilbert space, it's all vectors, so that when I actually move the operator to the other side, there's essentially a vector that implements this, like in a Riesz representation theorem. So you can define the adjoint as so. A symmetric operator is self-adjoint if the domain of the operator T is equal to the domain of its adjoint. And then there's this extra condition that comes up in the Hilbert C-star module setting, which is called regularity. So I won't get too much into why that's important, but one of the reasons why this assumption is pretty important is that Voronowicz and Napierkowski showed that there is a functional calculus for regular self-adjoint operators on Hilbert C-star modules, and that functional calculus is vital to looking at anything regarding integrability. So, okay. I'm running a little short on time, so I'm sorry. I'm going rather quickly here. I wanted to, maybe I'll just write down not the formal theorem statements, but if you have questions about them after I'm done, we can talk about those. So we did need some tools to come up with an integrability criterion, namely some just classic operator theory tools that we have in the Hilbert space setting for self-adjoint operators. So in the Hilbert space setting, you know that an operator that is symmetric and densely defined is self-adjoint if and only if you look at the range of these subspaces and they are dense in the Hilbert space. This is known as like the criterion for self-adjointness. And we got an analog of that for regular self-adjoint operators. Not too hard to show. Okay. The second major tool that we utilize a lot, and I've mentioned already for the Hilbert space setting, is Stone's theorem. And there's been some work on this. Leonard and I have been looking to try to see if what we've proven is actually new. But we do at least know in the case where you have a regular self-adjoint operator, it does generate a strongly continuous one parameter group of unitaries using that functional calculus. And if you have a strongly continuous one parameter group of unitaries on a Hilbert C-star module, it generates a self-adjoint regular operator on a Hilbert C-star module, on that same Hilbert C-star module. So we do have a generalization here. And then the last major theorem that Leonard and I needed for our result for integrability was Nelson's analytic vector theorem, which says, again, that you know an operator is self-adjoint if and only if it has a dense set of analytic vectors. And we were able to get that result as well, but in the setting of regular self-adjoint operators. And I do welcome anybody who is an expert in this area and you guys actually know that some of these results exist somewhere. We'd be happy to see them. We just haven't found them yet clearly written in the literature. Okay, so last thing I wanted to say is that here's what Leonard and I have shown. If you have a Heisenberg pair that acts on a dense submodule K of a Hilbert C-star module, and K contains a dense set of analytic vectoration to a Heisenberg representation. So this is a generalization of what Leonard showed in terms of the Flato-Simon integrability criterion result. And applying this, we do get, in the case where we have a Hilbert K of H module, that AB is unitarily equivalent to a direct sum of copies of the Schrodinger pair, which I didn't define for you, but P is the infinitesimal generator of the unitary group representation U that I showed you from the Schrodinger representation, and similarly Q is the infinitesimal generator for the unitary group V that I showed you previously. And with that, I will end. Thank you.